Welcome to this explainer. Today, we're diving into a massive, honestly fascinating topic all about the periodic table and classification of elements. Subscribe, like, and share my channel, JEE Concept Galaxy, as we go on a mission to completely demystify how we organize the very building blocks of the physical universe. We're going to see exactly how scientists took a totally chaotic world of varied substances and decoded the underlying physical rules that govern absolutely all of them.
So here is our roadmap for today. We'll be hitting the early laws of matter, Moseley's atomic breakthrough, taking a look inside the atom, exploring the modern periodic table, and finally looking at the predictable trends and elemental properties.
All right, let's kick things off with Section 1, Early Laws of Matter. Let's start with the historical foundation, right? How did we even begin organizing the physical world around us? Well, long before we knew anything about protons or quantum mechanics, scientists were just trying to make sense of how stuff mixed together. Early pioneers, like Antoine Lavoisier and John Dalton, formulated the very first laws of chemical combination. They realized that matter wasn't just some random chaotic dust. They discovered that atoms of different elements actually combine in really strict, fixed ratios to form pure compounds. Plus, they figured out that chemical reactions don't create or destroy atoms. They just separate, combine, or rearrange them. This was a huge paradigm shift. It basically meant there was a hidden rulebook to the universe.
And this brilliantly illustrates the ultimate truth, famously summed up by the legendary physicist Richard Feynman. He basically pointed out that the theoretical rules of chemistry, the rules of how substances combine that Dmitri Mendeleev originally summarized, are actually driven entirely by fundamental physics. Chemistry isn't magic, guys. It's literally just quantum mechanics in action. But to get to that realization, scientists definitely had to stumble through a few early mistakes.
Which brings us perfectly to Section 2, Moseley's atomic breakthrough.
So early chemists made a highly logical, but actually slightly incorrect assumption about how to order all these new elements they were finding. For a long time, elements were sorted strictly by their atomic weight. And that makes sense, right? Line them up from lightest to heaviest. But doing that created these really weird anomalies in the periodic table's groupings. For example, cobalt has an atomic weight of 58.9, but nickel is 58.7. Going by weight, nickel should absolutely come first. But chemically, that totally ruined the pattern. It wasn't until we realized that the atomic number, the exact number of positive protons in the nucleus, is what truly defines an element, that the whole puzzle was finally solved. But how on earth did we prove this? Enter Henry Moseley. Between 1913 and 1914, he mathematically proved this underlying reality. He literally shot characteristic X-rays at various elements and measured their frequencies. When he took the square root of that frequency and plotted it against the element's position on the periodic table, he got a nearly perfect straight line. Boom. This proved definitively that there's a fundamental property increasing by regular whole steps from one element to the next. That step is the proton count, which we denote as Z. Moseley permanently fixed the sequence of the periodic table, rightfully placing cobalt before nickel because of its atomic number, not its weight. Let's dive a bit deeper in Section 3, inside the atom. To truly understand why the atomic number, those protons, matters so much more than weight, we need to zoom in and look at the anatomy of the atom itself. As Feynman so beautifully explained, we don't even really need the word carbon. Carbon is literally just element 6. Why? Because it's got a tiny, massive nucleus packing 6 electrically positive protons, surrounded by a cloud of 6 incredibly light, negatively charged electrons. And here is the absolute secret to all of chemistry. An element's chemical properties depend entirely on those outside electrons. The heavy protons in the center are really just there to dictate how many electrons are held in orbit. So the real kicker here is that you can actually change the heavy neutral particles inside the nucleus, the neutrons, without changing the identity of the element itself. We call these variations isotopes. Because isotopes have the exact same number of protons, they hold the exact same number of electrons. And because of that, they behave exactly the same way in chemical reactions. And this dynamic builds right into our next concept. What if two entirely different elements, meaning they have different numbers of protons, happen to weigh the exact same amount because of varying neutron counts? Well, we call those isobars. This perfectly highlights why arranging the periodic table by weight was a bad idea in the first place. Two completely different chemical elements can share the exact same mass.
And just to complete our rapid-fire atomic definitions, if different elements happen to share the exact same number of neutrons in their nucleus, but have different atomic numbers, we call them isotones. All these definitions show us just how incredibly dynamic the nucleus can be, even while the chemical identity of the element itself remains completely locked to its proton count.
Just look at this table. If we check out carbon's isotopes, its atomic mass can actually range from 10 all the way up to 15. But listen, no matter how heavy it gets, as long as it has 6 protons, it is still just element 6. Its chemical properties, whether it's sitting in your body right now or locked in a diamond ring, are totally identical, because that outer electron count hasn't changed one bit.
All right, moving on to section 4, the modern periodic table. Now that we deeply understand the microstructure of the atom and why the atomic number reigns supreme, let's zoom back out to the macrostructure. Mendeleev's early chart was just an absolute masterpiece of scientific intuition. He grouped elements by these strange, repeating relationships in their physical and chemical behaviors. Today, we know that these columns and groupings perfectly align with their electron configurations, specifically exactly how those outermost electrons are arranged.
Today, the modern table is this incredibly organized grid. It's made up of 7 horizontal periods, where each period begins with the filling of a new energy shell, and 18 vertical groups. More importantly, it divides these elements into distinct S, P, D, and F blocks. This block structure is entirely based on which orbital the final, most energetic electron lands in. Oh, and you'll probably notice the F block, the lanthanides and actinoids, are usually floating at the very bottom. That's not because they aren't part of the sequence, it's literally just a formatting trick to keep the periodic table from being way too long to print on a normal piece of paper. Kind of funny, right?
Let's wrap things up with section 5, trends in elemental properties.
Because of this strict electron-based grid, the periodic table isn't just some boring list. It actually acts like a predictive cheat sheet for how the physical universe will react. Depending on how you navigate the grid, elemental properties shift in highly predictable mathematical ways. If you move left to right across a period, the effective nuclear charge increases, which pulls those electrons closer. That means atomic radius and metallic character decrease, while things like electronegativity and ionization energy shoot up. Conversely, moving top to bottom down a group adds entirely new electron shells. The atoms get physically larger, meaning atomic radius and metallic character increase, while the pull on those outer electrons weakens, so electronegativity drops. It's literally a perfectly balanced matrix of physical laws.
So I'm going to leave you with this provocative thought. Feynman said that theoretical chemistry is in principle just physics. The periodic table is ultimately just a quantum mechanical rulebook for electrons. If that's entirely true, and we know exactly how these trends operate, how far are we from using computers to perfectly calculate every single chemical reaction possible? What entirely new, world-changing compounds are just waiting out there in the math, ready to be calculated into existence? Thanks so much for learning with me today, and as always, keep questioning the universe around you.